So I hope. Okay, so this is a continuous, this is a elementary, kind of very nice elementary mathematics with fairly rich history behind it. So you'll see. And this connects two important topics, of which Pell's equation still appears in the research sometimes. And this is a connection between Pell's equations and so-called continuous fractions. Maybe you have heard of them. If not, you'll probably understand from what I'll be discussing. It's very, very straightforward. It's also extremely old thing, which existed even before your usual decimal expansion of real numbers. Okay. So it's called continuous fractions, Pell's equations, two mathematical germs. Okay. Let's see. Okay, now Pell's equation is a Diophantine equation, meaning that it's an equation of which, so we only look for integer solutions. So you probably have learned how to solve a linear Diophantine equation with two variables in your classes. This is the first example of nonlinear equation in two variables, which is very nice and classical. X squared minus d y squared equals to 1. And d is an integer, which is positive integer, at least 2. Now, the first observation we make that if d itself is a square of an integer, then the only solutions for such equation would be x equals plus minus 1, y equals to 0. Because if we move dy squared in the other side, we get that the complete square should be equal a complete square plus 1. And this never happens, at least outside the case x equals plus minus 1, y equals to 0. Another observation is that solutions come in 4 tuples. So if x is a solution, if xy is a solution, then plus minus x plus minus y is also a solution. So if x and y are non-zero, then we get 4 solutions immediately, yes, from a single one. Okay, so we will assume that d is a positive integer, but not a square. Okay, now why is this equation interesting? It has connections with at least 2 very important areas of mathematics, at least classically important. The first one, I'll explain a little bit, and this would come later in the talk. It's a group of units in the ring of algebraic numbers in the quadratic number field Q of the square root of d. So let me explain what this thing is. So this ring we are talking about are all numbers of the form and rational number plus a rational number times the square root of d. A plus b, the square root of d, where a and b are rational numbers. This is called the quadratic number field. You can immediately see that you can add, multiply such numbers. And we'll be talking about that solutions of Pell's equation are so-called units in this thing. Units are invertible elements. I mean, typically, if we have a ring, yeah, let's say Z, we cannot invert. We cannot take in the ring Z, we cannot take the inverse of 5. Yeah, because it's 1/5 and it's not in the ring. But for example, there are 2 elements which are invertible in the ring Z, which is plus and minus 1. And they form a group under multiplication. You can multiply 1 by 1 and 1 by -1, and you are still in this set. So units in a ring are invertible elements, and they form a group under multiplication. So solutions of Pell's equation will be related to that. And also solutions of Pell's equations would be important in connection with approximation of numbers by rationals. This is also a very classical area. In particular, we'll be talking about quadratic rationals, where only square root of some combinations of integer numbers appear. And so that's what it says here, that if you have a solution of Pell's equation, x squared minus dy squared equals to 1, then you can also deduce that the absolute value of the square root of d minus this quotient x divided by y is fairly small. It's smaller than 1 over some constant y squared, where this constant has nothing to do with x, y, or d. So that's important. So you can approximate the square root of d by rational number fairly well. So this approximation of real numbers by rational numbers, it's a big area as well. It's related to proving that certain numbers are non-algebraic, do not satisfy algebraic equations. And there are a lot of open questions in this area you've probably heard of. It's known that P and E are transcendental, non-algebraic, but there are a lot of numbers which you can form where you would guess that they are non-algebraic, but there are no means to proving that. And one of the typical tools in this area is approximation by algebraic numbers and how quickly such approximations converge. Okay, so sorry, I'm getting distracted a little bit. So the equation was named after British mathematician John Pell from the 17th century. And this is one of the typical mistakes. And my former advisor, Vladimir Arnold, had a saying that if some object or notion in mathematics is called after a certain mathematician, this is because this person has never considered such a notion. Now, this is again such an example, but later, much older. So John Pell, was a British mathematician, but he has never worked on those things. And it was Leonard Euler who, about 100 years later, attributed this wrongly to Pell. And so this equation has a long history. I'll jump over some slides to show you some history here. I don't have an access to the TeX file. So here is some special cases in the 18th century. German mathematician Lessing, which should be supposed to be more well-known than he is, because he was the one who started the famous area of mathematics called topology now. He never got the credit for this here. He was also interested in history and mathematics. And so he found some very ancient manuscript where the mathematical problem, it more or less is solving a special case of Pell's equation for d equals this horrible number with 15 digits. And this the solution was found more than 100 years after that. And we'll discuss, so this we'll talk a little bit about the fundamental solution of this Pell's equation. And they are also, you see there are some even older sources discussing special cases, of course, of Pell's equation from the 17th century India, 11th century India, and then 16th century France, and finally 18th century Euler. He was Swiss by origin, but he worked most of his life in St. Petersburg. And he's probably the most prolific mathematician of all times. His collection of works is over 50 volumes. Okay, now we go back to our main topic, and let us start with the simplest case, where d equals 2. Yes, so we look at the Pell's equation x squared minus 2y squared equals to 1. And if we substitute x equals 3 and y equals 2, we get 9 minus 8 equals 1. So 3, 2 is a solution. And now we do a funny trick. We're looking at the numbers in the form 3, which is this thing, plus 2, and now the square root of this constant d, and then power n. If we do this, if we take 3 plus 2 times square root of 2 power n, and now decompose it into integers, and integers times the square root of 2, we get xn plus yn square root of 2. And the claim is that it's not very difficult to check. In fact, it's a nice exercise to see that xn comma yn would give us a solution to Pell's equation. And in fact, if we look at all those things with plus minus signs, we'll get all the solutions of this equation. So we have infinitely many solutions, but they are very structured. They are kind of in the form of z mod 2 times z. So they are up to these sign things, they are labeled by this power n. And that's what we're going to eventually discuss later. Okay, now we'll be reinterpreting solutions of Pell's equation in terms of this ring. Okay, once again, so we're looking at numbers. So q of the square root of d, that means that we're looking at numbers which are a rational number a plus a rational number b times the square root of d. And now we'll be defining a kind of involution on this ring, which is similar to complex conjugation. So we'll be sending a number a plus b square root of d to a minus b the square root of d. We'll be kind of changing the sign of the imaginary part. And now to any number psi like this, we'll be associating kind of, the norm, which is the square of the absolute value in the complex numbers. Namely, we'll be taking psi times psi prime. Similar to complex conjugation and absolute value. And if we do that, we'll be getting, if we're multiplying one by the other, we'll be getting the norm of the number psi is a squared minus db squared. This is called the norm. And now if they think this is exactly Pell's equation, the left-hand side of Pell's equation, and to solve a Pell's equation means that we'll be looking for all elements with a and b being integers and such that their norm is equal to 1. So in other words, we'll be looking for solutions in z instead of q of the square root of d having norm 1. So again, we'll say that the number a plus b square root of d with a and b being non-integers now instead of rational numbers is a solution to Pell's equation if a squared minus db squared equals 1. Now observe that the norm of the product of algebraic numbers which we consider is equal to the product of the norms. And this will imply that if we have two solutions, two numbers of the form a plus b square root of d having norm 1, then their product will also have norm 1. That means that solutions of Pell's equation form a group under multiplication. Okay. Now the next thing to consider is, well, obviously for any d, we have at least some fairly trivial solutions. X equals to plus minus 1 and y equals to 0. And that we always get that plus minus 1 comma 0 satisfies Pell's equation. So the set of solutions for any d is non-empty, but these solutions are trivial, and the question is, does it have any other elements? We have discussed in the beginning, if d is a complete square, there are only trivial elements, no non-trivial elements. What about d being different from a square? Okay. And here is a result by Lagrange, a famous French mathematician who made a lot of contribution, especially to mechanics and to celestial motions. He has shown that if d is not a square, then there are non-trivial solutions for any such d. And there is the smallest solution, a plus b square root of d, which is bigger than 1, yes. And then all solutions to Pell's equation can be written in the form of that example we did for d equals 2. So we can take a plus b square root of d, take its nth power, and then if we want, we can expand this into a pure integer and a number, a pure integer times the number of d. So the first one would be called xn and the other one would be called yn. And xn comma yn will solve our equation. And we can also put plus minus sign in front here. And the claim is that this would be all solutions, the set of all solutions for if n runs over all integers. And it is in this way we see that the set of all solutions to Pell's equation PD corresponding to a number d is a group, multiplicative group, which is numbered by a sign and an integer. So it would be isomorphic to the product, direct product of the group Z2 and the group Z. Okay, now we'll move to continued fractions, which is a nice topic. Yeah, so okay, so one notion before we move further: the smallest number, a plus db bigger than 2, which solves Pell's equation, is called the fundamental solution, because using it we can produce all other solutions, and that's why it's natural to call it a fundamental solution. Here are some examples for different d. So as we maybe already discussed, for d equals to 1, 3 plus 2 square root of 2 is such a number. For d equals 3, 2 plus square root of 3. Then for 5, one can still do it by hands, 9 plus 4 square root of 5, but then it gets more and more complicated, this number. And for example, for d equals to 61, we get already fairly fairly long expression for this fundamental solution. And so the question is, of course, how to find the fundamental solution. An interesting answer to that is by using continued fractions applied to number d, so to say, things, simple expressions coming from a number d. But to explain this, I want to tell you what a continued fraction is. It's not included in our education, which is a stupid thing, of course, but there are many things like that, unfortunately. Okay, so first of all, I explain how to expand a positive. So a continued fraction expansion you can associate to any positive number. And this would be a sequence, in principle, an infinite sequence of positive integers. And in fact, this goes back, as I mentioned, before decimal expansion. So you can find it in very, very early sources before the Christ already. Okay, but now how do we think about continued fractions is as follows. Assume that you have a, say, number for simplicity, a rational number bigger than 1, so like 87 divided by 38. So you split it into the integer part and the fractional part. So the integer part would be 2. The fractional part would be 11 divided by 38. Now, so this fractional part is smaller than 1. Yeah. But what you do, you write it as 1 divided by the inverse, and the inverse would be bigger than 1. Yeah. So here we have 1 divided by 38 divided by 11. So this thing is bigger than 1. And then you repeat your procedure, meaning that you split off the integer part of this, which would be 3. And then you get again the remainder. The remainder is a number which is smaller than 1. In this case would be 5/11. And then you again invert it and continue. So you have this expression at this step and the remainder 5/11. You write this as 1 divided by 11 divided by 5. This becomes bigger than 1. You can split off the integer part and get the part which is smaller than 1 and continue. So the next, after this step, you get 2. You see what I have. You have the important thing would be the sequence of positive integers: 2, 3, 2. Okay, so and this would be the end of it, because now we have this sequence. So we don't need to do this anymore because we have an integer here. So we have 2, 3, 2, 5. So the number 87 divided by 38, you can encode by a sequence of integers 2, 3, 2, 5. It contains a complete information. You can go back and get 87 divided by 38 from this sequence. Yeah. Now let's try to do another example. If we take a rational number 137 divided by 44, the integer part would be 3. The remainder would be 5 divided by 44. You invert it, 3 plus 1 divided by 44, 5. You split off the integer part, you get 8. So you have 3, 8, and the result here is 4/5. So you invert it, you get 3, 8, 1 over 5/5. So you get 3, 8, 1, and this is already in prepared form, 1 divided by 4. So you have a sequence 3, 4, 1, 3, 8, 1, 4. So here is the way how to go backwards. Yeah, assume that you have a sequence of positive integers, 3, 2, 5, 7, 6, to which rational number this corresponds. Okay, well, we'll do the inverse procedure. So we take the last the last integer 6 here and make it into 1/6. Then we add this to the previous one. So we have 2, 10, 5, 7 plus 1/6. So this gives us 47 divided by 6. Now we invert this and add to the previous one. So we have 5 plus 6 divided by 43. And this we keep so far. So we get 210 and this guy. Now we invert it and add to 10. So we're here. So this sum is this 2253, 221 divided by 221. And then the last step, we just add it to the first number. And after that, this is our answer in the form of a usual fraction. So we can go back and forth between continued fractions and rational numbers. So this is, for example, what happens if we have some sequence of positive integers and add another positive integer. So how things will be going. So here we start with 3, 7, then add 15, then add to 15, 1, and we'll get this 22/7, this, and then this, and they will be, this would be bigger than that, would be smaller than that. Okay, now we were talking about rational numbers. Now what about irrational numbers?
Ask a question.
Yeah.
Is there a way to multiply the sequences so that it corresponds to multiplying fractions?
No. So it's yeah. So continued fractions are very good for approximations, but they do not have so nice algebraic properties that you can handle them so easily. Unfortunately, not. At least not that I know. Yes. Okay, so here I want to mention that for usual rational numbers, this continued fraction decomposition will always finish. It will be a finite sequence. This is in general not the case. Well, this is never the case, I'm sorry, for irrational numbers. For irrational numbers, you will always get an infinite sequence of positive integers they correspond to. For example, this is a very nice example, square root of 2 plus 1. So this is 141, plus 1 would be 241, and so on. So you split off a 2, and the remainder is the square root of 2 minus 1, which is about 0.41. You take its inverse, 1 over this thing. Let's see. So this is the, yeah, so this says, sorry. So you represent this. So the inverse to square root of 2 minus 1 is the square root of 2 plus 1. So this is a valid representation. Square root of 2 plus 1 equals 2 plus 1 over the same expression. And then you just repeat this because we have it already for this thing. So you see, we'll be getting on the next step 2 and 2 here, and again repetition. And you can continue this as long as you want. So what we get is that the square root of 2 plus 1 with this process will correspond to an infinite sequence of 2's. Okay, yeah. But what does it mean that we have an infinite sequence of 2's? And there is a way to, I think I'm getting, yeah, so time is running away. I'm still not very close. So yeah, so Okay, so you can stop this process, say, after some number of steps. And what you'll be getting a sequence of positive integers, and this remainder would be some real number bigger than 1. And you have your identity that your number A you start with, so equals to, say, the first integer A0, which is its integer part plus 1 divided by xi1, or after 2 steps you have A0 plus 1 over A1 divided by 1 over xi2, and so on. Yeah, so you have a sequence of equalities where the length of the sequence of positive integers will be increasing, and then you have some real number bigger than 1 after that. So these are called convergence of the number A, because the length of this thing can be longer and longer. And there is a result saying that if you look what you get if you throw away this last real number, you'll get a rational number coming from a sequence A0, A1, blah, 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 An. And this sequence of rational number, what you can show that the sequence of rational numbers will be converging to a regional number N, A, and moreover, all even convergence would be smaller than A, and all odd convergence will be bigger than A, so will be alternating. A little bit smaller, a little bit bigger, smaller, bigger, smaller, bigger, smaller, bigger, but in the limit converging. And there is also an estimate how this alternation from the number A can be bounded from above. Okay, so in any case, we can associate to real number, positive number A, this sequence of integers, infinite sequence of integers in general, if A is not rational, and it's called a continued fraction expansion. Okay, let me see. Okay, so we were saying that a rational number corresponds to a finite continued fraction expansion. Now there is a very nice result about continued fraction expansions, which are periodic or eventually periodic. It can have some non-periodic part, but then periodic. The period starts and it repeats to infinity. And these are called quadratic rational numbers. Okay, so there are some examples. Okay, so here is the result which we want. That if we have some number alpha, which has a periodic, eventually periodic continued fraction expansion, meaning that there is some non-periodic part, B0, B1, blah, 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 Bm, and then there is a period A0, A1 through An, which is repeated then after that. So this overline here means that this fragment will be then repeated to infinity for our number. And the claim is that alpha is then a solution, is a root to a quadratic equation with integer coefficients. So A, B, C, yeah. And so it's a very nice criterion. Unfortunately, such numbers, quadratic rational numbers, are, they're not, it's not such a big class. Okay, now we want to go back to our topic eventually. And the next result is that if we pick a positive integer d, and now look at the number of the form, the integer part of the square root of d plus the square root of d. So this is a non-negative integer, and this is also, so this is an element of this ring Q of D. Yes, or even more, it's an element of this Z of square root of D. So it's a non-negative integer plus the square root of D itself. And now the claim is that if we look at its continued fraction expansion, this would be purely periodic. So, okay. And this is an example. If we take d equals to 7, then its square root would be a little bit bigger than 2. The integer part of the square root would be 2 plus this thing. And if we run this procedure, we'll be getting 4 and then 1s. But I wonder, is it a mistake here then? It seems like it has non-periodic part which starts with 4, and then it's just ones would be repeating all the time. Okay, now I want to finish this. Okay, so let me go on. At least we're not very far from there. So if we denote by capital D the integer part of the square root of D, and now take the number a, which is this integer part plus the square root of d, and then take its expansion. Then it's a claim here that a naught equals 2d, and the number a here not quite following. Anyway, let me tell you what it says. It says that if d is the integer part of the square root of d, let us look at the rational number which has this expansion d, and then a1, a2, blah 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 till to an, and call this p1 divided by q1. And now we take the other number a2, which has has the same beginning, and then we add 2d and then repeat a1 through an once again, and call this other rational number p2 divided by q2. Okay, and the claim is, and we can continue, meaning that the next one, a3, would be d. It would be a2 to which we append 3d and then the period itself. This would be p3 divided by q3. Okay, so now the claim is that pq squared minus dq squared is almost 1 up to a sign. Okay, now the connection to Pell's equation is the following finally. So that the first number, P1 and Q1, which we defined here, would be give us the fundamental solution if n is odd, n is the length of the period, and if n is even, so this then the second thing, P2, Q2 would be the fundamental solution. Is it okay? And so finally, there are some examples of that. Yeah, and this, I guess, is it. So the end is, I'm not so happy about the end. Okay, now I'll finish this, and I maybe again split you into groups. You can download this, and I give you maybe 15-20 minutes to go through it and see what was okay and what was less okay. Good. Now I'm stop sharing. And let me again, I stop recording.